So welcome back. It's good that most of you survived. Who tried to do any exercises? So did you succeed, David? Which one did you do?
I did the programming one, the last
Oh,
one.
great. So someone did the programming one. Do you want to share what you saw, or like say what you saw, or maybe you just remember what you were supposed to?
I can, if I let me see if I can find it.
So then I probably should stop sharing, right? And then you share, right? Oh. But while Avent is trying to share something, so you remember we sort of agreed on how we could try to solve differential equations using some very natural, very simple numerical method that we called Euler's method. That was basically saying that at each point I take all the derivatives of my variables and I multiply them by time step, and then I add them to my current state of the system. All right. Okay. So what Avent has done here, maybe he wants to say something.
Yeah. So if I actually didn't remember completely the exercise, but I think it was something like this.
Yeah, it was something like
this
that.
Hamiltonian.
And we also agreed that kind of any
I,
Hamiltonian looking like this would do the job.
Yes. So I drew some level sets here just to see what they look like, and I think you showed us something similar in the lecture.
Yes, yes. So this is what we drew by hand last time and by Google in the 3D space, right? Mm-hmm.
Yes. And then the Hamiltonian equations of motions should look something like this.
Mm-hmm.
And then I just made some like Euler method implementation of this system here.
Yeah, so precisely what we discussed. Yeah, and I guess this is the trajectory, right? Some
yes, that's
coordinate of velocity or something.
Yes. So we just we can change some starting points here. If you take 1, 1, for example, look like this, and here is like the step size. And try some different things. And then if we try to plot this in the same plot as the level sets, so I need to save this. To work?
Yeah. Oh, I actually see already the picture I would like to see. And I don't know, probably all the others also do. Like you see this circle that is a little bit deformed, and you see that the trajectory doesn't exactly hit the initial point. It sort of misses it, right?
Yeah. So if we do lower or a bigger distance between the steps, it gets much worse. You know, so.
Yeah. So you see, if you have the time step which is even more than that, then it starts really doing some non-physical stuff. Okay, great. You actually did a better job than I did. I mean, I drew some picture, but yours is, yeah, yours is maybe even more spectacular.
Oh,
so
thanks.
is the message clear to the audience? Okay, maybe let me try to share back my screen. Thank you. Oops, no, this is not what I wanted to do. Okay, this is what I wanted to do. Yeah, so what I did was a little bit less impressive. I just draw the dynamics. So okay, the picture you are seeing is for the harmonic oscillator, but the qualitative behavior for the pendulum is more or less the same, up to a little deformation of the circle. So what you are supposed to see here, I start from some point in the phase space, and this is where the level sets were living. So you want to see a circle here. And on this right plot, you want to see some kind of oscillation. Now I launch the video, and this is not what you see, and this is precisely the same that you just saw with Avent. And the question is why? Like, why the miracle didn't happen? You remember what I told you, that we are actually approximating the integral, right? So we are trying to compute the solution of a differential equation, and at each time step, you will produce some error here, right? Either you will underestimate the value or overestimate, but you kind of almost never get to the exact point. And when you look at the phase space, right? So this is the part of the trajectory you want to see. And you are somewhere here. Now, where is the, where can I draw the right-hand sides here somehow? What do I mean? We agreed that differential equation is a vector field on the phase space. So can I draw this vector field? Well, that works more or less like this. So at this point, I will draw an arrow, which I try to draw being tangent to my curve. Okay. And this is the thing that I will use to compute my next point. So this is my Q and Pn. And we agreed that Qn plus 1, Pn plus 1 is computed by the Euler method. So that will be Qn plus delta t. Well, I will write Qn dot, but Qn dot, we remember what it is from somewhere here, right? It is just dH over dP, and Pn dot is minus dH over dQ. So Qn dot is dH over dP plus here delta t. Okay, I will, just to be pedagogic, I will write the minus sign here because it's not, so it's still plus the finite difference, but if it turns out to be a little bit negative, so dH over dQ. But I need to tell you at which point I'm computing this, right? Because this is a function. So, and we agreed that we had no choice but to compute it at the point that we already know, right? Now, what is this dH over dP minus dH over dQ vector on this picture? This is precisely that, right? This is dh over dp minus dh over dq. And when I multiply it by delta t, I just take some finite part of it. So what I get, this, maybe let's mark it somehow. So this green part is this. So what I'm getting is this point is qn plus 1, p n plus 1. And you see, I kind of immediately went off the level set. So in the continuous world, I was just traveling on the level set, and now in the discrete world, immediately I go off it.
So you mean you go off the curve, right?
Yes, I go off the actual curve. So I make a small mistake. And what you have seen in Evans animation is that if I take a time step delta t, which is small, I go off, but by a little bit. If I take it large, then I just completely derail. What does it mean in this picture? Well, you see, in this picture, we kind of approximated the integral. Well, it looked more or less okay. Yeah, you have some small mistakes here, but at some point they start compensating. In this mechanical example, they are actually not. So what happens, I will draw just one of them, like, okay, let's say Q, or whatever. In the picture, it was probably the velocity, so let me draw a P. Anyway, it's schematic. It means that the actual part of the curve, you remember there was a combination of sine and cosine. So at some point it behaves like that. And when I'm doing this approximation, yeah, okay, I want I want to draw it the other way around, I think. Yeah, I mean, whatever, we will see it. So when I'm doing this approximation, I will be underestimating that all the time. Or there will be another part of the trajectory where I will be overestimating it all the time. So actually on a big portion of the trajectory, my errors, they don't compensate themselves, they add up. Okay. And this is actually a typical situation. I mean, if you compute an integral of some function which is sort of monotonous, then obviously taking all the time the left or the right approximation, you will gain some error. Is there any way to cure that? Like what would be a naive thing?
To make the steps like smaller.
Yeah, okay, that will certainly work in a sense that you will reduce the error. One small thing is that when I give you a mechanical system, you actually don't know what is a small step. You don't know what is the characteristic time scale of your system. But yeah, that's something that would work if you already spotted the fact that your system behaves somehow abnormally. The first reaction you should have is, okay, let's reduce the time step. Let's reduce the discretization parameters if you're doing PDEs. But you need already to identify that something is going wrong. Because obviously I'm giving you a simple example, but if I give you something very complicated, like the molecule. You remember the first day we were talking about molecular dynamics. It will still move somehow. So the idea is, let's try to imagine a more generic solution, some numerical method which behaves better. I mean, I will not specify what it means, behaves better, but which is just nicer in some sense. The question is, what is our freedom? Because how I presented it last time, I think you had the impression like, okay, we have no choice, right? And I even more or less phrased it like this. I said, look, I want to compute these areas, but I actually don't know much about my system. So the only thing I can do is draw these rectangles and go to and fro between coordinates and velocities. Well, I sort of lied to you a little bit. Because actually, no, I can try to choose a different point in this integration business. And then I will have some conditions. For example, instead of this one, I can say I take, this is still equal to x of t, but now instead of computing v at x of t, I will compute it at x of t plus delta t. Can I do this explicitly? No, because I don't know x of t plus delta t. But that will give me some relation between them, right? I know this guy, I know this guy, I know this function explicitly, so I can compute it at each point that I want, but I don't know these two guys. These two guys are the same. So actually I have an equation, an algebraic equation here, some kind of f of x of t plus delta t equals 0. And if I'm very lucky, I can solve this equation by hand. Or if I'm not lucky, and this is also a part of the numerical analysis course, I will solve it approximately, but maybe with a better approximation than just saying, okay, my x of t plus delta t is x of t. And this is also called an Euler method, but implicit Euler method. Implicit Euler method. So again, I'm still in my computing the integral business, and now I'm trying to do it using the right points instead of the left points. So it means that in this case, instead of taking Qn and Pn here and Qn and Pn here, I will always take Qn plus 1 and Pn plus 1 in the right-hand sides, and here too. What would be your expectation? Does it help? Does it cure the thing? Well, let's see. Let's see. So the explicit Euler was doing this, right? It was spiraling and the energy was increasing. Now the implicit Euler does this. Well, still no luck, right? It still spirals. It doesn't close the loop. And actually now when I show you this, you would probably tell me that this is natural, because what I actually did is, instead of underestimating the integral, I'm always overestimating it. This picture, right? And I'm always underestimating this on this picture. So I'm again accumulating the error in the same direction. But then a pretty natural idea comes into the game. Why don't we mix them? So for one of them, I will take the endpoint, and for the other one, I will take the beginning point. So let me choose another color. And I think the easiest option would be to say I'm computing everything at Qn and Pn plus 1. And the other one would be also Qn and Pn plus 1. So I am implicit in the momentum, and I'm explicit in the velocity, in the coordinate. Okay. So kind of semi explicit. And this guy is actually called symplectic. Again, let me show the animation. Well, looks better, right? It's still the same time step, but you see, at least naked eye, you see that the level set seems to be preserved, and the oscillations go as they're supposed to go. And again, I was just waving hands. I say I underestimate, I overestimate, and now I want to kind of combine the two. That was maybe an educated guess, but actually there is some science behind. And historically, it was indeed sort of guessed like this. And now when I say historically, it's not 1700, it's more like 1960s or 1950s, when people just started doing numerical simulations. So when the computers back in the days took room, and just following the tradition, people started computing the trajectories of the planets. And they realized that the same phenomena that I just showed you happens with you when you apply some basic methods. They realized that, okay, we can reduce the time step, but then the computation takes a lot of time. And they also realized that these implicit methods are a little bit more stable than the explicit ones. Stable, what does it mean? It means that, let's say you take two trajectories, two initial conditions that are close to one another, and you launch the simulations for two of them. And you look at the trajectories. I mean, obviously, if things are nice, like everybody is smooth and all the functions are not too ugly, these trajectories should not drift too far apart one another, at least at some time period. This is not what people observed in the computations. They realized that even some small perturbations for a complicated system like the planetary movement does make the trajectories drift too far apart. And it means that if you gain some small error at first time step, then probably you just get a totally different trajectory. That's not good. You're launching satellites, you want to kind of predict what's going on. And they did it with explicit stuff. They saw that with implicit stuff, it's a little bit better, but still not great. And then it was just an idea, more or less like I presented it, let's mix the two. And they realized that that was working much better. And then maybe 10 or 20 years passed before people realized that the explanation is actually that there is some geometric structure which is preserved, more or less the same geometric structure that Lagrange guessed back in the days. And this is actually my second exercise. Did anyone but Avent try to solve it? So my second exercise was this. I was saying that I have my phase space and I have some geometry in it. I have some differential equation, or it's the same, a vector field that respects this geometry. And I wanted to say something about conservation laws related to it. Did anyone give a thought to it? Well, I agree that this is a little bit tricky also because it is formulated in a very vague way. So let me be more specific. So maybe the topic would be something like from symplectic forms to energy conservation. What did we have? We had an object which we call the symplectic form that was a differential 2 form, non-degenerate. Non-degenerate meaning that when I plug in something, the only way to get 0 is to plug in 0. And closed, so the omega was vanishing. And I said that we give ourselves a vector field, V, vector field, that was preserving omega. And preserving, well, believe me or not, preserving means the Lie derivative along the vector the vector field V of omega vanishes. So, okay, this thing. And I was asking more or less 2 questions. First, let's say I have this, and can I say something about conservation of energy? So, question H, energy, is it conserved by the flow of V? What would you say? I mean, the only data is this. The short answer is a priori no, right? A priori no. Actually, just look back at whatever face portrait you want. Okay, I lost my face portraits. Here they are. You are somewhere here, and you have a vector field that preserves some geometry in the game. Fine. Does it have to preserve the level sets of all functions? No. It only preserves the level set of function of the function that define the dynamics. So if your energy has nothing to do with the vector field, then it has nothing to do with the vector field. Like In this picture, that would mean that I have some vector field. I don't know. Let's put it like this. It is still maybe Hamiltonian with respect to some other Hamiltonian that is different from my energy of the system, and then a priori there is no way of saying that. But I still meant some positive answer to this, and let me formulate the question. So given this, can I find an energy that is conserved? Question in the chart. Yeah, so what we understood last time is that if the energy is the same Hamiltonian that defined the vector field, then it is preserved. If it's not clear, and the generic citation just not. Okay, I will now formulate the cleaner result. So what I want to find is actually some function that will be a Hamiltonian function for my vector field V. Okay, and what do I have as the conditions? So let me spell out this guy. It was, as before, the contraction applied to the exterior derivative of omega plus exterior derivative contraction omega. Okay, I'm supposed to write V here. Sorry. Up. V. And I'm saying that this is vanishing. Okay, this is vanishing by itself, right? Because of that. And this is a condition. So remember, omega is a two form, right? This contraction iota V omega, which is just the same as omega computed on V with another slot left. This is a one form. And I have a one form which is closed. So let's call it maybe alpha. I have d alpha that vanishes. And having this condition of existence of the Hamiltonian would mean that alpha is actually d of something. So this is what I want to study. And the answer to this is related to what people called cohomology. So if there is no cohomology at this degree, and for those who don't know what is the cohomology, I'll just write it in words. So if there is no difference between closed and exact forms, then there exists such an H. Okay, so you might remember this probably from Avian's talk, that if you have this operation D of a form, you apply it twice, this always vanishes. So if my form is D of something, then D of this form is necessarily zero. And so this direction always works. In this direction, not necessarily, but cohomology precisely measures the difference. So if there is no cohomology, and this is a geometric property of the space you are living in, then you can always integrate. When the spaces are to n, that's fine because there is no topology. So this is one point. If I have a vector field which preserves the symplectic form, I can eventually find its Hamiltonian if things are nice. This is one message. Another message, now, suppose I have found this Hamiltonian, what can I say about it? So now I have this condition. Suppose this thing is verified. So my V is actually a Hamiltonian vector field with respect to H. Then what happens with this H? Well, let me just compute it. I want to see if my energy is conserved. So this is before I will apply the Cartan's magic formula, and there is actually just one term because I cannot plug a vector field into a function. There is only this term. Again, I'm writing X. I'm supposed to write V. But this guy, I know from above, I have something like that. Twice the contraction of the vector field with a differential form. So this is something like omega computed 2 times on the same vector field. And this, you know that this vanishes because omega is skew-symmetric. So when you compute it 2 times on the same object, it always vanishes. Okay, I realize this is probably a little bit mysterious for people who have never done differential forms before, but then just a take-home message. Take-home message. First, a vector field preserving a symplectic form can give rise to a Hamiltonian. So it can be written in the Hamiltonian form here if some conditions are verified, some conditions. Now, if V is Hamiltonian like this, then necessarily V preserves the level sets of H, the level sets of H. Okay. And this is actually the thing that we would use in numerics. So instead of directly preserving the energy of the system, I will construct an integrator that will automatically preserve the geometric structure. Now, if this sounds a little bit mysterious, let's try to interpret this in small dimension. So interpretation in 2D. I'm in R2 and I have a 2 form. What is the geometric meaning of it? So I have some operation that it's up, at each point, it's up 2 vectors, which is non-degenerate. multilinear and skew symmetric. What is this guy? If you did your linear algebra class, then you should be able to answer to me. Right, I repeat, so at each point, I eat up two vectors. I'm multilinear and I'm skew symmetric. Who am I?
Is it a cross product?
I'm still in 2D, right? The cross product
Well,
in 2D,
yes, actually, yes,
but you are not far from being right. Right? What is the meaning of the cross product? I mean, the appropriate part of the cross product when you project it back to 2D.
the area of.
Yeah, exactly. Yeah. So actually, what I was meaning is determinant, but the real answer is this is the area of the rectangle, right? So and this suits me well. So actually, what I have, omega, is the, I have to say, oriented area in R2. Well, at each point of R2, but I'm not willing to spell this out. And I say oriented because I want to keep track of the sign, right? If I'm skew symmetric, I permute my two vectors, I get a negative, I get a minus. And what I just wrote above is basically the following. I have some dynamics in my phase space on my R2 that preserves the area. What does it mean preserving the area? That now I don't have, I'm not taking one point and I look at it. I take a small region around this point and I look how it behaves. Now let's try to convince ourselves. It's not a proof, but it's kind of what qualitatively happens. Let me look at some regions like this. This one, now a bigger one, which includes it, and another one. My dynamics preserves the area of all of them, right? So I will eventually somehow deform the picture. Well, I mean, it's already deformed enough. So I can have some dynamics and for every region of this space, its image will have the same area. What I'm actually saying is that the deformation picture I drew is wrong. Right? I can deform it somehow, but I will still stay inside the regions. And it's a little bit difficult to prove with elementary tools. And actually, the regions I drew would not be enough. I would probably have to take also some regions in this direction, right? To convince you that actually I can move inside the regions, but I should not go outside the regions. And then that would precisely mean that I preserve the level sets. So you see the difference, for example, between the blue and the green region is this small band, right? And if I make it even smaller, then I kind of collapse to the level set, to the value to the given value of the energy. So this is kind of the waving hands way to show that we preserve level sets. Okay. Well, I hope this is a little bit more convincing than just a long fancy formula. Okay. And this is what precisely what happens in these simulations. So when I look at this symplectic order, let me look at this again. This we can check. Well, it's a little bit more tricky to run the simulations for that, but we can check that now I will take a small region here, for example, and look at how it deforms. I will see that it does deform, right? Because the points that are here should move a little bit faster than the points that are here. So I might have this cloud kind of breathing, but I will for sure know that when it comes back, it will have the same area, and it will still stay close. And this is what guarantees that in my previous picture, okay, this is the wrong picture. My previous picture here, the errors actually start compensating at each step. Okay. Well, this is the philosophy of geometric integrators. I look at some geometric structure and I see what does the preservation of it mean for the dynamics of the system. I'm going back to the slides. And this is what we have seen, right? My geometry was given by the symplectic form, and we were able to extract the equations of motions from it. And these equations of motions were preserving the symplectic form and automatically were preserving the level sets, so the values of the energy functions. The same thing can be done with the Poisson thing in the continuous world. And this is actually where tricky things start happening, because when you type in Google symplectic integrators, you get a lot of references. When you get Poisson integrators, you have much less. Now, did we agree that those are important? Yeah, that's kind of a question you shouldn't ask no, especially after 3 hours of struggling through it. But let me just give you two thoughts about it. Look, we were on this phase portrait, a very simple system. But if I now start drifting with the energy, right? I was on my compact trajectory. I was oscillating around the equilibrium solution, and now I have this explicit Euler that start spiraling the thing. Then at some point, I will cross my separatrix, right? There will be a time step when I cross and I exit the compact region. And then my qualitative picture kind of collapses. I was oscillating and now I start rotating. I do implicit methods, it goes the other way around. So I was rotating and my energy starts decreasing, the trajectory starts shrinking, then I go this way. Well, you don't really want to see it. It's not the physical behavior of the system, so it means that your computer modeling sort of failed. Now, here you would say, oh yeah, okay, it's strange. It was oscillating, then all of a sudden there is a phase transition, it started rotating. And you would say something goes wrong, then I need to look at it carefully. But now if you start with a system which is a little bit more complicated, right? We started with a system that was more complicated. You are not sure that you will spot the phenomenon. Like now think of a long molecule, some kind of protein that contains 10,000 atoms. And at some point it was moving one way and then it folded into some other configuration. Biologically, it would probably mean that some protein in the brain of a cow changed the conformation. So mad cow disease. You want to be sure if this is due to your simulation or this is actually happening in nature. And I'm saying this is important for molecular dynamics because actually this is where you can determine what is the nice time step. But when you do determine it, you are not very happy, because the nice time step is the one that captures the small oscillations of atoms everywhere in the molecule, which is about a picosecond. But the trajectory that interests you is about a second or two. So this is something which happens in the macroscopic world. Now imagine you're doing 10 to the power 9 steps, and at each time step, you are making a small error in energy. Well, there is a very good chance that your system in the end has nothing to do with the system in the beginning. And you probably created all possible numerical artifacts you can imagine. Okay? Again, this is a little bit of a propaganda, but this is something that happens in life. And actually, people in molecular dynamics also realize that pretty fast. And if you take a molecular dynamics package, there will be just a checkbox. Use the Verlet method, the velocity leapfrog method. And that one is symplectic. Well, biologists don't know that. They're still using it because that gives you a better quality simulation. Okay? So is up to now the message kind of clear? Fortunately or unfortunately, I don't know, this is not the end of the story. This is the beginning. So remember, I showed you this table. And as promised, we just did the first line. This is the first line that is older than probably most of you in the audience and also older than me. So people started doing this symplectic business in the 80s. Then they obviously realized that not all the systems are conservative, and not only the conservation of energy is important. So for instance, the video that I showed to you, this wavefront, well, it's obviously dissipative, right? That interacts with all the things around, but you are not interested in the energy of the wave. You are interested in the symmetry of the wave. And this is the whole different business. Maybe you will see some of the mathematics around this, especially Lie groups and algebras and the Cartan calculus, in the lectures by Jan next week. Then you want to make several systems interact, and this is my third line in the table. Then the correct geometry is what people call Dirac structures. And in Gradec, there is a specialist in the house. I mean, he's probably not connected, but Alexei Kotov is the one from whom I learned this Dirac business. Then you can think of open systems or control systems, and apparently the word foliation is appropriate there. And all this is in finite dimension. Now you go to infinite dimension, the picture is even more intricate. Some geometric objects are even not really defined, or you need to struggle through infinite dimensional manifolds. But still, there are some partial results. So more or less, the motto still holds. If I'm able to preserve geometry, then there are good chances that I will do something nice to the physics of the system. More or less in every situation, there is a different approach. For every different geometry, there is some technique that helps you. How explicit it is, well, it's a good question. So this is what I mean by saying it's the beginning of the story. Okay, let me maybe just finish with some references. It seems that the tradition is to give some references. So if you want to go further, if you want to get more details, there is a text which is probably one of the the Bible sources about geometric integrators. This is a book of Heyer, Lubitsch, and Werner. At least all the symplectic business I told you and some more is there. Now there is the variational counterpart to this picture. So if you are more familiar with variational principles, then the Marsden-West book is more or less for you. They talk about mostly Lagrangian dynamics, also in a very large collections of situations. Now, these two references are to pretend that we are as great as these guys. So these are my colleagues who started the symplectic business a little bit closer to actually formulate a theorem, like what happens in the discrete world and what you can actually prove in the discrete world. Because what we did today was more or less observe, right? And I was saying you don't see the difference naked eye. But actually the details inside are rather intricate. Because what happens is that a lot of things you are used to in the continuous world, they fail. Like differentiating composite functions, this is not the same. Leibniz is no longer satisfied, but it is satisfied up to some order of discretization. And if you want to make these things properly, if you want to formulate a mathematical theorem about what I just said, that would not be conservation of symplectic form implies preservation of energy. That would say conservation of symplectic form implies preservation of energy up to some order in the time step, and this preservation holds for this long in the trajectory. Okay, this is this third paper. And the fifth paper is some kind of survey that we did about other geometries, not necessarily symplectic things, but more or less the table I just showed you, there are some more details in it. This is not about scientific results, not necessarily scientific results that belong to us, but this is kind of an overview paper that covers a little bit in more details what can go right and actually what can also go wrong, and what are the geometries that we think are nice to study. And there is also one text in Russian, but it is actually finally translated to English, where we wrote something for computer algebra people. So actually we vulgarized all the geometric concepts to more or less vector spaces and matrices and all this stuff. So maybe to start this is not bad, not bad as a reading. Okay. And also I'm available for questions and comments and even after the school is finished. So if this topic somehow interests you, there is a lot of stuff to be done. And even if you are not a senior person, if you are a student, there are still some small things you can contribute to. So if this kind of excites you, do contact me, we will find something to talk about. Okay. I think I'm done for this lecture and for this mini course. I'm happy to answer the questions. Maybe let me stop the recording just to